Hello everyone, ThA17 is talking to present the joint work with Dr. Q Marcy. The topic of this presentation is safe control design of systems operating in uncertain environment using barrier functions. Here is the outline of the presentation. I'll go through a quick background, motivation, and then I will represent the approach we took to solve this challenge. There are many different factors that affect the safety of control systems. These constraints might be from the system limitations itself, like the actuator saturations or mechanical constraints of the system, which results in some sort of state constraints. This might be from the environmental constraints, like when a car is driving in a shared road with other vehicles and needs to adapt to the flow of the traffic. Or consider the shared workspace of robots. Robots have large area to cover, but because they shouldn't collide with other agents, it kind of limits their workspace. Also, the safety of nearby objects, and especially human operators that are working nearby, should be guaranteed. When we have some sort of constraint, like the limits on the set or some even nonlinear relationship between different states, these constraints form a set in which inside the set, the safety specifications are satisfied. Therefore, one of the strong tools to handle these constraints are control barrier functions, which ensure the forward invariance of the set C. And what it means is that if we have some initial condition within the set, we can make sure that in the all future times, the state of the system would stay in this set. And how this control barrier function works is kind of similar to control Lyapunov functions. I give this example to make it closer to mind. Like if we have a Lyapunov function v, which its derivative is negative and the level sets are constantly shrinking, this enforces the trajectory to converge to the origin. We have some similar story here as well. Assume that we have a function h, which is positive within the set and 0 at the boundary. Now, if we have a positive derivative at the boundary, when the trajectory gets close to the boundary, h dot becomes positive, therefore h increases and the trajectory of the system will be pushed back inside the set and the safety will be preserved. Okay, assume here is our system dynamics and here is the safe set that we have, which is written based on a safety criterion h equal or bigger than 0. H itself is a barrier function candidate because it is positive within the safe set and it's 0 at the boundary. Now, to have a safe operation, we need to make sure that h dot is positive at the safety boundary. Therefore, what we do, we use this barrier function criterion. If you see here, if h gets close to 0, then h dot becomes positive. One of the great advantage of barrier function is that it can be added to the controller that we already have. Assume that UHAT is the original controller that we have. It can come from LQR or any other control methodology. We try to find the closest control policy to our original controller such that the barrier function condition is satisfied. And if you take a look at this condition, U appears here like in a linear relationship, and this optimization is easy to solve. But one of the challenges here is that if you take a look at h dot, the trajectory information x dot appears here, then we need to have full knowledge on f and g, which is not always available in practice. So we need to investigate the effect of uncertainty and also uncertainty in the environment. The focus of this presentation is that how we can have a safe controller for a system which is working in a shared environment with other external agents. These external dynamics are unknown, pretty much uncontrollable, like you really can't control the behavior of pedestrians in a road, and also it's unpredictable. On the other side, their behavior is very hard to model, especially when we have human behavior in the loop. And still some unpredicted dynamics might be observed, like jump of animal in the road or some other unpredicted behavior. The other challenge is that prompt reaction is needed. We don't have enough time for online complicated training. So the motivation here is that we would like to have some learning enabled barrier function, but we want to make sure that even if we have some, quick rough learning scheme, this inaccuracy doesn't lead to violation of safety. Okay, here is the problem formulation. Assume this one is the dynamics of the ecosystem. Here is the external dynamics, which we assume we cannot control. And the safe set is defined based on the both states of the system and external dynamics and Z. And if we write the barrier function condition, you see that Z dot appears here, which we don't have access to. So what we do, we employ neural networks to learn about these external dynamics. We derive the recursor form, and using that, we find the estimation error, and we employ this update law to learn the network. I won't go through the detail of this learning. You can find it in the paper. And what I want to say here is that, okay, we try to learn this external dynamics, and we can define an approximated safe set using that learned information. However, due to learning inaccuracy, C hat might not be exactly on C, and we have some sort of error. And if we directly use the barrier function to make sure C hat is forward invariant, still the original safety boundary might be exceeded. So the idea here is that, okay, let's ensure forward invariance of a subset of C hat such that we make sure that the boundaries of C is not exceeded. Then as the learning enhances, C hat converges to C. And the subset we are working on is actually the intersection of the safe set and its approximation. And the thing is that I give you an example that that when the pedestrian are walking through the road using, sensory observation, like from LIDAR or other stuff, we know the distance, but we don't really know what's next. We don't really know how it behaves. So we have actually access to Z, but we don't have access to Z dot. Therefore, we are able to form this set. Then we define a new barrier function, which employs the dynamics of the learned model, but shrinks the boundary using instantaneous sensory observation to avoid imminent risk. And here is the overall configuration that we work on. We observe the states of external dynamics. We learned about its trajectory, and we applied our observation and the trajectory information to the barrier function, which is employed as an inequality constraint to the controller. And using this control barrier function, we show that CC, which is the intersection of the safe set, and its approximation is forward invariant, which means the safety of the system is preserved. The overall overview of the proof is that we use Nagumo's theorem. Based on this theorem, X dot should be within the tangent cone of the safe set at the boundary, which means the X dot should point inside the set or be tangent to the boundary in the worst case. So we find that intersection, and we derive its tangent cone, and we show that if we use this proposed barrier function, that intersection set would be forward invariant. And the importance of this method, well, we propose some learning-based barrier function and extend the application of barrier function when really we have uncertainty in the system and in the environment. And we examine how we can safely operate when the environment is cluttered and uncertain. The other important thing is that we have safety during learning. So C hat does not need to be accurate. We just need to have some rough approximation. Therefore, some simplified model also can be used, and therefore it enables rapid reaction. And even if we see unexpected dynamics, we are able to, handle it even with some conservative action. We can still be safe. Okay, the simulation results are is on a lane changing problem. Here, the safety objective is that beta be kept below z. Z is our external dynamics, which is modeled by a simplified model with a simplified network. And here are the simulation results. If I explain what's going on here, this dashed line is the beta, which should be kept below this dotted line. This dotted line is z. And this yellow line is the approximation of that external dynamic z. And if you see here with just an LQR solution, the safety is violated. Now we examine the barrier certified method with non-zero reconstruction error and with zero reconstruction error. And as we see in both of the cases, beta is kept below the external dynamics and the safety of the system is ensured. And if you see here, what it's actually doing is that here we have a large error between the dynamics and its approximation, but the safety is ensured. And beta has stayed below the more conservative one. Like here in this one, the approximated one is smaller than the actual value of z, and beta has respected this one. So we take the conservative action, and safety is ensured despite the learning error. And here are the other states of the system. The lane is changed and other variables has converged to zero. While the design of learning enables safe control design in uncertain environment is examined, and we have safety during learning with even simplified modeling. And the future work includes includes safety aware learning, which tries to expand that intersection for providing more room of safe action. Thank you so much for your attention.